Okay, so hi everyone. Welcome to our second lecture in the course Competition, Policy and Strategy, which is based on my 2020 lecture in of the course Wettbewerbspolitik und Strategie at Justus Liebig University of Gießen. In this course, we're talking about oligopoly models. Recall that last time we have been looking at the two other extremes, which is perfect competition and monopoly. So these situations contain some notion of competition, but here we look at this in much more detail. And we present two workhorse models in economic theory, which is Bertrand and Cournot competition. Before we get into the topic, please like the video and subscribe to our channel to help us grow and to support the creation of our content, which we think is quite valuable as we make available university lectures basically to everybody. Okay, so oligopoly. When we talk about oligopoly, we talk about a situation where few firms compete and there is strategic interdependence between the firms, which means that when one firm makes a decision, it takes into account the response of all other firms, right? When they make their decisions. And in that sense, we assume that firms play a game in the sense of game theory. Right? And game theory is basically a formal analysis of players' strategic decisions, and it helps us tremendously when we want to analyze competition between firms here. When we look at game theory, we have to look at game theory concepts and some basics before we start talking about oligopoly models, as you cannot, basically in modern economics, you cannot basically do anything serious in microeconomics without having a good understanding of game theory, and especially in competition economics and industrial organization, you're basically completely lost when you don't have these basics available, right? And that's why we dig into that a little bit, even though the basics should be known already, as this is something that you have in your basic micro 101 lectures. Even though this is formal, the formal analysis of games should be devoted to a separate course, and there's several available on the internet, as well as you can look everything up in a basic textbook. So if we talk about a game, then we think of four things, and that is players, actions, payoffs, and information. That is what defines a game. Players is the set of players in the game, basically, and here we assume that we have n players. Actions is what the players can do, right? And this is a little bit more sophisticated when we define this mathematically, as we have to think about strategy profiles, which in our applications here in this course is rather simple, as it basically says what you do. And again, it's basically a single number or a single decision, whereas if you have more sophisticated games, it's a profile of different things that players can do. And a strategy profile contains all available strategies of that player. It's basically a strategy set that we're looking at. So this sigma I is the strategy set, and we talk about the strategy profile as one element of this set. Then when we extend that further, when we just take the Cartesian product of this strategy set of each player, then we are at the strategy space of the game. So it's basically the space that defines each strategy profile combination that we can have in the given game, right? A payoff is what the player gets from choosing a certain strategy profile given the strategy profile of the other players, right? So it's a function, the payoffs are a function of sigma I, which is the strategy profile of player I, and a function of sigma minus I. And sigma minus I, that minus I here is defined as all players except for player I, right? So what all the others do except for the player that we're looking at. And we usually assume that's a real valued function. The payoffs function is usually we assume that it's real valued. It makes analysis much more tractable in a sense. The last thing that we have to define is information. Information characterizes the timing of the game. In principle, a game can be simultaneous or sequential. And as the name suggests, a simultaneous game is characterized by players choosing their actions simultaneously. And sequential game is a game where they act sequentially, right? It could also involve uncertainty, right? Risk or whatever. And this is a draw of nature, basically. So nature would be a player, and that player just randomizes at a given stage. You can, of course, combine all these different concepts to have, players choosing sequentially first and then simultaneously, and then you could have uncertainty and whatsoever. So it could be a combination of all these things. Usually our games are either sequential or simultaneous, and what we will do today is basically just looking at simultaneous games. Okay. Usually, when we talk about game theory in a very classical sense, we assume that players are rational. And that means that the players, given their preferences, act optimally. So they are optimizers. And that's called internal consistency. Rationality can go further than that, right? So especially when we look at behavioral economics, we depart from this rationality assumption in various aspects. So sometimes the players make mistakes. Sometimes they have preferences which are reference point dependent, right? So probably they have loss aversion, stuff like that. We abstract from that at this point here, because that usually leads to situations where we have to, so mathematically it gets more complicated, and we also need much more basic background to tackle that, even though, and that's very important, these topics, especially departures from rationality, play a huge role when we talk about decision makers in general. So it would be completely naive to assume that every decision maker in reality is rational. And that's something that is part of modern economic research, but goes beyond what we want to do here, right? Another thing is the term common knowledge. And here we assume that rationality of the players is common knowledge, which basically means that every player knows that all other players are rational, and every player knows that all other players know that every player is rational, and so on and so forth. So that's depending on how often you play, you repeat that term, all players know that all players know, you get to an N level of common knowledge here. That's something that is game theoretically, against the background of game theory, there's studies on that, but again, goes beyond our topic, right? But you have to have that ready here. We are in a basic setup, everyone is rational, and rationality is common knowledge. Okay, then we have our Nash Equilibrium. Goes back to John Nash's work, which was published in the early 1950s. And the Nash Equilibrium is basically the most important notion that we rely on in modern game theory, even though you can refine that Nash Equilibrium in various ways. And here we just use this most simple definition here, and that is that a strategy profile is a Nash equilibrium when all players choose their best responses based on all other players' best responses, right? So basically, when every other player behaves optimally, you behave optimally as well, right? And if you do that, then we are into Nash equilibrium. What is the best response? That's a very crucial part. So best response, best reply, however you want to call it, is basically a profile, strategy profile, that maximizes your profits given some strategies that the others choose, right? So that's the best response to a certain strategy of the others, right? So you maximize your profits over your strategy, and what is the result is a best response function. And when we look at the Nash equilibrium, mathematically speaking, we have a fixed point of these best response functions. So basically, where all best response functions intersect, we are in a Nash equilibrium. In other words, when we are at a point where each player plays its best response and no one has an incentive to deviate, we are at a Nash equilibrium. That's the general concept. And I think it is useful to look at this concept now in a Cournot setup, right? To really understand what it means, right? Okay, so now we get into our first fundamental concept of competition, and that is Cournot competition. It is named after Cournot, who lived from 1801 to 1877, and the basic concept here is firms compete in quantities. That's why Cournot competition is usually also referred to as quantity competition, even though that's quite simplistic. It's a simultaneous game, right? There's a sequential game of quantity competition, and that's usually referred to as Stackelberg competition. Technically, it's somewhat different, and prediction-wise it is as well. And now we just rely on Cournot competition. So the very basic workhorse model of economics, of I/O and competition economics is Cournot competition. And to analyze the basic functions of this Cournot competition, we take a very, very simple example as a starting point. And that is that we have identical firms with constant marginal costs, right? So here we have a cost function which is the same for each firm, that is characterized by constant multiplied by our quantity. So we have no fixed costs. Recall from our first lecture that the cost function is comprised of fixed costs and variable costs. And the fixed costs here is 0, because there is no term that basically is 0. And we have a constant here that is multiplied by our output, which basically means that marginal costs variable costs are C times Qi, and marginal costs are the derivative of that with respect to Q, and that's C, right? So our variable costs, our marginal costs are constant. And small c, that's the constant, right? And that's the same for every player. We assume that demand is linear and takes the form A minus B times Q. Capital Q here. And capital Q is the industry output, right? And I have kind of abused notation here as we have assumed here, or denoted P of Qi, and we will see where Qi appears here in a minute. We assume that goods are homogeneous. It's relatively easy to introduce differentiated goods in that setting, even though that's something that should be done in a separate instance, and that is done in the I/O class that Georg has recorded, I think in 2021, and it's available here on Economics to Go as well. So once you have listened to this lecture and you're interested in heterogeneous products or differentiated products, you can look this lecture up to see more on that. The game is one shot. So you don't repeat the quantity competition. We will have a huge set of videos. It's basically a single lecture but it involves multiple classes, multiple videos here, where we talk about repeated games. Basically, the thing is that here we assume that firms meet once and then the world ends. But that's usually not the case in reality. In reality, you compete a year and then you compete the next year and so on, and you anticipate that when you do something today, it affects the payouts tomorrow, right? So, and in that situation, things get more complicated. But here we abstract from that because we want to focus on the general mechanisms of that static one-shot competition. Okay, I've told you that I have used notation, and how did I do that? I will just assume that the total output in the industry, capital Q, comprises of Qi, so the output of firm I, and the output of all other firms minus I. Recall that the index minus I refers to all other firms than I, all firms except for I. So our total output is, when we look at firm I, that what firm I produces plus that what all others produce, right? So Q, capital Q, is the sum of Qi and Q minus I. And once firm I makes a decision, right? So we are in a game theory context, it takes into account what the other firms do. And now we take a look at the central part of where we get to our equilibrium prediction, and that is the profit function, right? So what we want to do is maximize profits to get to an equilibrium. And when we maximize profits, the crucial part is, of course, the profit function that we're maximizing that determines what happens in the market, right? And we know that the costs of the profits pie of firm I are a function of what firm I produces and what firms minus I produce, right? And this interdependency between firm I and the other firms is captured by the inverse demand function here, because the inverse demand function depends on the industry output, and the industry output depends on what firm I produces and what firm minus I produces. And that's this term here, function P as a function of Qi and Q minus I. And there we have our main difference between our perfect competition and monopoly models that we had before. So recall that in perfect competition, this function here was a constant because each firm was a price taker, right? So there was just a constant price P. In monopoly, there were no other firms. So we only had P as a function of Q here. And here, and that's why I was defining these two things as extremes on a line, we're moving inside this line here, and we are assuming that there is competition between the firms. So, and that means that mathematically speaking, that inverse demand function is a function of what I produces and what all other firms produce, right? Now, if we try to compute the optimum here, we just differentiate this function with respect to Qi. And what we do is how this looks like is basically that we have the partial derivative of this inverse demand function with respect to Qi times Qi plus the price as a function of Qi and Q minus I, just multiply this and differentiate it. And what is also left in this first order condition is minus C, right? And that C we just move to the other side. So what we see here is the first order condition basically rearranged such that we have a equation that tells us that the profit of firm I is maximized when marginal revenue is equal to marginal costs. We know that should always be the case. And here the marginal revenue is basically comprised of a competitive effect and a price effect, basically. So again, quantity effects and price effects as in monopoly. However, this is now a partial derivative and not as it was in our monopoly case, where it was simply a derivative because that inverse demand function now depends on another variable in our model, right? And that is Q minus I. And now in order to elaborate on that further, what we do is that we assume that we have a certain type of inverse demand function. right? So again, we have assumed that it's linear and it takes the form A minus B times capital Q. And what we now do is to just substitute as for our capital Q, Qi plus Q minus I, so that we are at this inverse demand function. And now if we just differentiate this inverse demand function with respect to Qi, we get to minus B, right? So here we have minus B times Q plus our inverse demand function, which is this one. So we get to plus A minus B Qi plus Q minus I. So what we basically end up with is this equation here. If we just rearrange the resulting expression with respect to Qi, right? And this is what we call, so the first order, again, just recall what we did, right? So we took the profit function, noting that capital Q is Qi plus Q minus I, plug this in, differentiate this function with respect to Qi, set the resulting equation with such that it equals 0, rearrange with respect to Qi, and you end up here. And what you get is a function that basically connects Qi and Q minus I, right? And this function is the best response function. And why is it the best response function? It was derived from the first order condition. So whenever this function determines Qi, we are in a profit maximizing point, at least with respect to Qi, right? So this tells us how for every Q minus I, so for every given behavior of other firms, how should firm I set its output to maximize its own profits? So how should it react optimally? Well, according to this function, right? So if you observe a Q minus I, or anticipate a Q minus I, then you just plug it in here and you get what I should do in order to maximize its profits. And in order to understand that, we should look at what is called residual demand. Residual demand basically just tells you how much is left for a given firm I when all other firms have produced their output, right? So the blue one here is our total output, and the orange one here, so more yellow-orange, is the residual demand of firm I. So it's basically shifted inwards by what the others produce, right? And what we do in Cournot is to just take the marginal revenue based on this residual demand, set this equal to C, and determine output and profits, prices, and so determine output by that. Okay? In order to get a better understanding, we assume for the moment that we have two firms, right? And we just go back to our best response function and assume that we have two firms, and then we get to the function that we have here, because Q minus I now is only, go here, Q minus I. If we look at firm 1, this Q minus I is simply Q2. So what firm 1 produces as a function of what firm 2 produces, right? And this is the best response function. So it basically tells you how much should firm 1 produce given that firm 2 produces something, right? And now assume that, just to get an illustration of what this basically tells you, assume that firm 2 produces so much as it would produce in perfect competition. So where price equals marginal costs. And this is A minus C over B, right? So this is the output firm 2 would choose in perfect competition. And if this was the case, how much would firm 1 produce? Well, just look at this. Just plug in here A minus C over B, and then you see that this best response function is equal to 0, right? So if firm 2 produces the output that would occur in perfect competition, firm 1 would not produce. anything, right? Because it would incur losses. On the other hand, suppose that firm 2 is not active, so it produces 0. So assume here Q2 is 0, then the output of firm 1 would ideally be A minus C over 2B. And that is exactly the monopoly output, right? So you have connected with the Cournot oligopoly that we have just analyzed our perfect competition and our monopoly cases that we have learned, that we have get to learn in our first lecture, right? And the Cournot model that we see here, it has an equilibrium exactly where the two best response functions intersect. Why? Just recall our Nash Equilibrium concept. The Nash Equilibrium was basically defined as the intersection point between the best responses. And now we have two best responses here. And the two best responses, where they intersect, is where we produce, where we have our Nash Equilibrium. And this intersection point, or the quantity that occurs then with symmetric firms, is here what we call QC. That's the Cournot output in equilibrium. How can we obtain that? Well, go back to the general case where the number of firms is just a positive integer. However, assume that firms are symmetric, right? So we have imposed that assumption in the beginning. If this is the case, then we can assume that firms produce the same output in equilibrium. And if we assume that, then we can say that the output that all other firms except for firm I produce is the number of firms minus 1 times the output that firm I produces. I think it's illustrative to use an example here. Suppose we have 10 firms in the market, and suppose that we look at firm 3, right? So our firm I is firm 3. Then what is the total output that all other firms produce? Well, according to this equation, it would be 10 minus 1, so 9, times what firm 3 produces. So all firms produce the same, and what all other firms produce in total is what firm 1, 2, 4, 5, 6, 7, 8, 9, 10 produce. And the number of firms, except for firm 3, is 9, right? And that's why we have n minus 1 times qi here, as this is equal to what the other firms, except for firm I, produce in total, right? And what we do is to take our best response function here, sorry for sliding through the slides, we just substitute for q minus I our n minus 1 times qi. And what you end up with, you should do this as an exercise, and it's basically also done on our tests, our online tests. Just substitute this and rearrange with respect to qi. What you will get to is this term here, right? You get as an intersection point between the reaction functions, given that all firms behave the same, well, because they are symmetric, we get our Cournot equilibrium output, which is 1 over b times a minus c over n plus 1. And this is the output that all firms produce in equilibrium. How can we check that? Well, plug in QC in QI's best response function, and you will see that QC will be the results, right? So there's no incentive to deviate. Use QC, multiply by n, and you get industry outputs. And from this industry outputs, you can get to the price. And there's one crucial thing here that has to be stated absolutely clearly, and that is the firms in Cournot produce outputs, and the law of one price and choose, right? So there is one price in the market. In Cournot, you don't set a single price per firm. You have one price in the market, and that price is determined basically, you can say, by market clearing. So once every firm has produced its output, then consumers get there and buy that stuff, and we get an ensuing market price, right? And this market price is the same for every firm. So one market price in Cournot. And the market price looks as I have depicted it here for our given example, right? So just take QC, multiply by N, and insert into the inverse demand function to get to that point. And you can insert this price into our profits and consumer surplus, and you get into to the equilibrium values of profits and consumer surplus. Again, you should practice this and just insert, take the given example and calculate it. And you can also use given numbers, and we have certain tests on that will be online to help you. Okay, so that was the basics of Cournot competition. And what we now do is to look at Bertrand competition, which is basically the other workhorse model that we have in economics, right? Bertrand competition is named after Bertrand, who lived from 1822 to 1900, and basically he assumed that firms compete in prices and not in quantities. So that's the crucial difference here. What this means is what we will see in a minute, right? And again, to get an understanding of how this competition mode functions, we assume that we have identical firms, right? So again, identical cost functions. We have homogeneous goods. We don't repeat the game, so one shot. We have no capacity constraints. I will discuss that towards the end of this lecture. And we assume that we have two firms. Why? Well, it makes the analysis much more easy than if we assumed multiple firms, not because the economics get more complicated, but because the graphical illustration and the mathematical treatment get more complicated, right? So we assume we have two firms here, just to make the thing more tractable and more easy to assess. Okay, so what is the basic idea of Bertrand? Basically, it says that consumers buy from the cheapest firm, right? So if you have, let's say, 3 olive oil stores next to each other, and you see that there's basically the same olive oil in all 3, and you say, okay, at firm 3 or at shop 3, I can get my olive oil for $4.99, and in all other stores it's €5, so I go to shop 3. And all consumers do that. And we have assumed that there are no capacity constraints, which means that shop 3 can serve all consumers in the market. And that, in consequence, leads to the low-cost firm, the lowest price firm, to serve all consumers in the market, right? And that is basically what drives the results here. And we will see why this is in a minute. We just assume that if prices are equal, so if all shops charge the same price, and if we have like 2 shops, each shop serves half of the consumers. So they allocate in the sense that market shares are equal, right? That's just an assumption. It makes the analysis easier, but it's not crucial, right? Unless the market share of each firm is positive in equilibrium, but that's just, we assume that to make it more understandable here. Now, given that mechanism and this assumption, we can compute the demand of firm I for 2 firms. How does the demand look like? Well, Qi, which is demand of firm I, is a function of the price of firm I and the price of firm J, right? So we haven't used the index minus I here because minus I would simply be 2, right? So we use J as we could also have said I is equal to 1 and J is equal to 2, but then we would have to do the same for firm 2. But here we just say that I and J are either 1 or 2 and I and J are not the same, right? That basically indicates all different combinations here, and the quantity of, or the demand of firm I is a function of its own price and the price of the other firm, right? And now we just have to look at this piecewise function here, which is fairly simple to understand, right? So just look at the first line here. What does it say? Well, it says that if we are in a situation where firm I is strictly cheaper than firm J, firm I gets the entire market. Why is that? Well, that's exactly the example that I've told you, right? So the two shops are next to each other, and in firm I, you can buy your olive oil for $4.99, and in shop J, you have to pay €5. So everyone pays $4.99 in shop I, right? Go to the middle line here. There you have a situation where the two prices are the same. So in shop I and in shop J, you have to pay $4.99 for your olive oil. And in that case, half of the consumer go to shop I and half of the consumers go to shop J. That's what we have assumed so far. You could just assume that this is just a fraction of them, but here basically the demand for each shop is positive. Now, the last line here is basically the reverse situation of the first, right? So if shop J or firm J is more expensive than firm J, if firm I is more expensive than firm J, nobody will buy at firm I, right? That's why demand is 0 if firm I is the high price firm. And there you get your demand schedule. Based on that, you can set up profits by the same token. You basically multiply by pi I minus C, right? So your profit function as a function of the own price and the price of the other firm is if firm I is less expensive than firm J, you have the entire market demand at price at price pi times pi minus C, which is the revenue or markup. It's the markup or profits per sale. And if you match the price, if the two prices match, then you have half of the market demand for each firm times price minus costs. And if firm I is the high price firm, it won't sell anything, right? Now, we can intuitively find our way to the equilibrium. Suppose, start looking at marginal cost first. You can easily say that no firm will ever charge a price below marginal costs. Why? If you did so and you sold anything, you would make losses, right? So you would never choose a price below marginal costs. So the low bound is, of course, price equals marginal costs. You cannot go below that. If a firm chooses a price above monopoly prices, then the other firm would undercut and set the monopoly price. Why? Look back at our concept of monopoly. A monopolist is somebody who maximizes profits, right? And the monopoly price is the price that maximizes industry profits, given that we have a single firm. So you cannot do better than to choose the monopoly price when you want to maximize industry profits. And if the other firm chooses a very, very high price, you respond to that by setting the monopoly price, because the monopoly price maximizes industry profits and the other firm is basically behaving completely strangely, so you can just grab all the consumers with setting the monopoly price. So get a better understanding. Assume that the monopoly price is 80 and assume that the price in the market, that the rival sets a price of 100. Should you undercut your rival slightly? No, you can just set a price of 80 because that's the monopoly price and you serve all consumers with a monopoly price, which basically says that you realize the monopoly profits, and the monopoly profits are the highest profits you can incur in the market. So you can realize the market, and that's why the best response if your rival chooses a price strictly above the monopoly price is by you to choose the monopoly price, right? In other words, you shouldn't see a price above monopoly prices in the market because it's completely nuts, basically. Now, that we have determined a lower bound and an upper bound, the interesting thing is what happens in between. So what happens between everything that is above marginal costs and below monopoly prices? And if you are at a point that is with an open interval above marginal costs and a closed interval at or below the monopoly price, your best response to these prices is to undercut your rival, right? So if firm J sets any price in this interval, firm I would undercut the price slightly and attract all consumers, right? What does this mean? Well, if we assume that the monopoly price is 80 and the marginal cost is 20, for everything above 20, strictly above 20, and at or below 80, you will undercut. So if your rival sets a price of 80, you set a price of 79.99. And you can respond to that by setting a price of 79.98. So that's what your rival will do, right? And that will just lead to a spiral of undercutting. Keep in mind here that this epsilon is arbitrarily small, and we usually assume that prices are real valued. That means that we're not talking about 79.99, but we're talking about any arbitrarily small undercutting, right? So it's not the case that we are in a euro world or whatever worlds where we have two digits. So it's basically, it's an arbitrarily small number below that, right? Below the price of the rival. So based on this scheme or this reaction, we can formulate a reaction function. So what is Pi as a function of Pj? If your rival chooses a price above monopoly prices, so here in the upper part, we just respond by setting the monopoly price. If your rival chooses a price in the range above marginal costs but at or below monopoly prices, you undercut the rival's price by a very small amount. And if you are at a price equal to marginal costs, you choose a price of marginal costs. And you immediately see what the equilibrium is. It is price of each firm equal to marginal costs. So the intersection point of the reaction functions is exactly here, where each firm chooses a price equal to marginal costs. How can we explain that? Or how can we get an understanding of that, right? So you know that the highest possible price or the highest useful price is the monopoly price. From the monopoly price, you undercut, right? And the firms play a simultaneous game, so they anticipate that for every price above marginal costs, you will be undercut. You will not go below marginal costs, as this would lead to losses. And since you anticipate that for every price above marginal costs, you will be undercut, and every price below marginal cost leads to losses, then the only price that we can anticipate to not be undercut, to have still sales, is price equal marginal costs, right? And this is what we call the Bertrand paradox in economics. And that is, there's other Bertrand paradoxes, whatever the plural is here, but there are others, and in economics it indicates a situation where two firms are sufficient to generate an efficient market outcome, because two firms are sufficient to get to a point where price equals marginal costs. Recall our first lecture, where we have just stated that welfare is maximized whenever price is equal to marginal costs. And here we see two firms are sufficient to get to that point, right? So that's kind of a paradox situation, because it would basically say that we never have a problem whenever we have at least two firms in the market. Is this realistic? Well, probably not. We will talk about this in a minute. Here you see a graphical illustration of what I just told you regarding the Nash equilibrium in Bertrand competition. So the orange line is the best response function of firm 2, the blue line is the best response function of firm 1. Both functions have an upper limit of PM, where they don't go above, and they have a lower limit of C, which they don't go below. And you see here that the best response functions intersect exactly once, and that's where price equals marginal costs. Okay, now we just compare the two models. In Bertrand, we have basically established that we have allocative efficiency, and we have just analyzed a single situation with a single setup, no capacity constraints, no uncertainty, one shot, and so on and so forth, right? So under these conditions, we see that Bertrand yields an efficient result. And in Cournot, we have prices above marginal costs as long as we don't have infinitely many firms, which is kind of the situation always. And what is important to note is that once we would arrive at a Cournot price, right, we would not anticipate this to be an equilibrium, because if the Cournot price would be observed and the firms would no longer be quantity setters, they would set price and they would undercut that Cournot price and serve the entire market. So it shouldn't work, right? And that's really like the heart of this concepts here. So that's how Bertrand, as far as I know, established its article. His article, he basically says that, okay, what Cournot wrote is just doesn't make sense, right? And that's that started a debate. I mean, it would have. I think it has started before, but that's what we basically see as the origin of it, of this discussion on how markets actually work. And of course, we have to ask ourselves the question: how does that relate to real-world examples, right? I think it is neither realistic to assume that you have two firms and everything works well, nor is it realistic to assume that we always are in such a Cournot world where firms strictly choose outputs. But it depends, of course, on the market we're looking at. And how can we get a better understanding of real-world markets? Well, first, we can think about differentiated goods, right? And we can think about firm I being a monopolist for its own right, right? And that's basically what we do when we are in a so-called hoteling model, or when we talk about vertical product differentiation, or horizontal, that's basically hoteling. And if you want to know more on that, just go to our IO course on our channel, right? Because then we have a lot of stuff tackling, on a lot of content on that. You could go also via the route of repeating the game, right? So it's basically not very realistic to assume that a market exists exactly once in time and then it's over, but usually it's the situation that you repeat a game, right? So they repeatedly interact on the market, the firms, right? And if you assume that this is the case, then we can have situations where collusion among firms organically emerges as a form of tacit collusion. But you could also have explicit collusion, and that's something we will talk about very much over the course of this lecture, because that is something that is, from a competition policy standpoint, very important. So collusion means cartel emerges. It could be tacit, it could be explicit. What this means, what we will learn later. But the consequence is that we basically move away from efficiency, even in a Bertrand setting, because the firm gets to firms set higher prices, anticipating deviation later would, undercutting, would lead to retaliation by the others in the subsequent periods, and that potentially stabilizes the situation where firms set high prices, even though we are, for instance, in a Bertrand situation where undercutting would be expected if we were not to repeat the game. Another point, and that's also very crucial, is capacity constraints. We have assumed that in Bertrand, one firm could serve the entire market. And in fact, from a purely theoretical standpoint, it would be enough to deviate from that by assuming that the firm is not able to serve the entire market at a price equal to marginal cost. Because that could lead us to a situation where if one firm sets a very low price equal to marginal cost, for instance, the other firm would still have residual demand, right? So think of a simple situation where we have two olive oil shops, and one firm has 80 bottles of olive oil and sets a price that it sells all these 80 bottles. But there are 100 consumers who wants to buy one bottle, right? So there would be 20 consumers left who don't get a bottle at that shop. So they would go to the other shop. And since the first shop that is already sold out, olive oil is already sold out there would be 20 consumers who have no other choice than to buy from firm 2. And what firm 2 would do is to increase the price, right? And it could do so because it cannot expect that the firms switch to the first shop, because that shop doesn't have olive oil left, right? And that's what we call, that's basically what we think of when we talk about capacity constraints. And that concept is called Bertrand-Edgeworth, because it's basically that's the economist Edgeworth who refined the Bertrand concept with capacity constraints, and there's more sophisticated models that emerge from there. And another important aspect in this case that is worth mentioning is the so-called Krebs-Shaman model, which was published in 1983 in the Bell Journal of Economics. And Krebs and Shaman basically combine the ideas of Cournot and Bertrand, in the sense that Cournot is the first stage where the firms just set up capacity, then they set prices. So first quantity setting as capacity setting, and then the firms charge prices, and then we have some allocation of consumers. And it turns out that under certain conditions, we can generate the Cournot outcome with such a gain, right? And it's much more realistic, because if you look at things from a more long-run perspective, then what firms do is to first think about, okay, I have a market here, and I want to serve that market, so I first build my production plant, and this production plant has certain capacity. So the first thing that I do is to plan how large this capacity would be. Given this capacity, I produce and set a price on the second stage. And if we do that in competition, then we might end up with a Cournot result, actually. What's also important is uncertainty about costs and demand, right? So if we are in a Bertrand setup and one firm does not know what the other firm's costs are, well, then things get more interesting anyway, because you have a prior and you interact, and then you update your prior, and then you see, okay, probably the other firm is more expensive than me, so I can charge high prices without problems, because the other firm is too expensive, cannot produce at the same price that I am, right? But that's something that is relevant in reality as well. Okay, so the last slide here is again supposed to help you to derive a Cournot equilibrium with a linear demand function, as I've just used in this slide. I will not go through that in detail, but you can look this up if you want to practice, and it will help you solve the exercises that we have put up to complement this lecture. Okay, then this was it from today's lecture, and thank you very much for your attention. Please leave a like and subscribe to our channel, and yeah, we see you in the next one.